By 1970, Douglas had built something the airline world said it needed. A widebody for the routes the 747 was too large to fill. Capable, modern, ready to connect continents, the narrow-body jets could not reach economically. The DC-10 looked like the future, but the pilots who flew it knew something the sales figures never captured. This aircraft was different on the ground, different at altitude, different most of all on approach. It demanded something specific from the crew at the controls, something no other widebody of its generation asked in quite the same way. The question was exactly what? The brief that came out of American Airlines in 1966 was specific, urgent, and pointed directly at Boeing's growing advantage. Douglas had watched the 747 launch order arrive and understood the calculation immediately. If they did not build a widebody for the routes, the 747 was too large to serve economically. Boeing would own the next decade of commercial aviation without meaningful competition. Americans' requirement was precise: an aircraft capable of carrying around 250 passengers, operating from the congested gate infrastructure at airports like Chicago O'Hare, flying medium-range routes at frequencies the 747's economics could never support, capable of generating a return on sectors where the 747's seat count and fuel burn made the numbers unworkable. The brief did not ask for a smaller 747. It asked for something designed from the beginning around the constraints the 747 had been built to ignore. Douglas had roughly 2 years to make that aircraft real. Douglas responded with a design. Lockheed responded with one of their own, and the competition that followed would define the wide-body market and nearly destroy both companies in the process. Both designs were trijets. Both targeted identical carriers on identical routes. Both arrived at 3 engines through the same reasoning. 2 were not enough for overwater certification under the regulations then. In force, and 4 added weight, fuel burn, and maintenance costs that made medium-range economics irrational. 3 engines were the answer. Douglas knew it. Lockheed knew it. It was the only number the market would accept. Where Douglas and Lockheed separated was in how they mounted the center engine. Lockheed buried theirs inside the fuselage at the base of the tail, drawing air through an S-shaped duct, the same solution Boeing had used on the 727. Douglas chose differently. Their center engine sat in an external pod at the base of the vertical stabilizer, fed through a straight intake. Cleaner aerodynamically, free of the distortion problems the S-duct created. Nothing quite like it existed in commercial service at the time, and the result was immediately distinctive. The DC-10's tall tail, the engine nacelle sitting above the fuselage roofline, became the aircraft's visual identity the moment it appeared on a ramp. The choice looked elegant. It was elegant, but it introduced a structural consequence that would follow the aircraft for every year of its operational life. The vertical stabilizer now carried 2 loads simultaneously: the aerodynamic demands of a conventional tail surface and the weight and thrust loads of a mounted engine. The attachment structure engineered to hold both was complex. It was certified and it worked. But it was complexity of a kind that demanded precise, practiced maintenance, and the aircraft's operational history would carry that requirement forward on every cycle it flew. American Airlines placed the launch order in April 1968. United Airlines followed. Continental Airlines placed orders shortly after. Douglas had customers before it had a certified airframe, and the commitment was total. The first flight took place on August 29, 1970, at Long Beach, California. FAA type certification followed on July 29, 1971. By the end of that year, the DC-10 was in scheduled service across the United States. What the airlines received was genuinely capable, range exceeding 6,000 nautical miles on later variants, payload capacity that made long, thin routes economically viable at frequencies the 747 could not serve, a wide twin-aisle cabin that offered passenger comfort no narrow-body could approximate, and a flight deck that, at first inspection, appeared logical, well-organized, and modern. At second inspection, it told a more complicated story. The DC-10's flight control system was hydraulically powered across every primary surface: ailerons, elevators, rudder, spoilers, all of it fed by 3 independent hydraulic circuits. The redundancy was real. Lose one system and 2 remained. The certification logic supported that architecture completely. But the physical routing of those three circuits through the rear fuselage and tail structure placed them in proximity to each other in ways that specific, severe failure scenarios could compromise simultaneously, not in normal operations, not on a routine sector. But in the failure modes that accident investigation examines with the most care, the physical separation between redundant systems was not always what the schematic assumed. Line pilots were not managing a hydraulic schematic. They were managing an aircraft, and at cruise altitude, the DC-10 was stable, solid, and capable. The wide fuselage absorbed turbulence in a way narrow-body crews noticed immediately on transition. Three-engine crews produced comfortable thrust margins without the fuel penalty of a four-engine design. The aircraft performed exactly what Douglas had promised it would. It was not a difficult machine to fly at altitude. It was a fundamentally different machine to fly on approach, and the pilots who flew it learned that distinction early in their transition training. The flight deck, however, carried more than two pilots could manage alone. Behind the captain and first officer, at a panel that covered the full right wall of the cockpit, sat the flight engineer. Their station was not decorative. It was not a backup position. Hydraulic pressure across all three circuits, electrical generation from each of four sources, fuel state across 12 tanks and multiple transfer systems, pressurization, bleed air. The flight engineer monitored and managed all of it, continuously from takeoff to shutdown. The DC-10 was not an aircraft two pilots flew while systems monitoring happened when time permitted. It was an aircraft that required a third trained specialist whose sole function was to understand the aircraft's internal state before the crew on the line ever needed to know something had changed. That requirement was not an admission of design failure, it was a philosophy. Complexity managed by a dedicated specialist was safer than complexity reduced for a smaller crew. The airlines accepted it. Training programs built around it. The knowledge a flight engineer carried on the DC-10 could not be simplified into a checklist reference. Without losing something essential, a generation of them built careers on a station that most passengers walking past the cockpit door never knew existed. The DC-10 went to work carrying that knowledge on every departure. It flew passengers across continents and oceans, operating routes the narrow-body era had never been able to serve at scale. And inside every cockpit, at every altitude and every phase of flight, the aircraft held something in reserve, a demand it had not yet fully made. The approach when it came would show exactly what that demand required of the people flying it. The DC-10's behavior in cruise was something pilots came to understand gradually, and over time, to read with precision. At altitude, the three CF6 or JT-8D engines produced a yaw tendency managed by twin hydraulic yaw dampers drawing from separate circuits. The system functioned as designed, but the aircraft flying itself through calm air at 33,000 feet and the aircraft being managed through turbulence, system degradation, or asymmetric thrust conditions were not identical machines. Cruise was where a crew met the DC-10 on its own terms. Approach was where those terms became non-negotiable. The energy management problem began well before the threshold. As the crew configured the DC-10 for arrival, flaps extended in sequence, slats out, gear down in the final miles, the aircraft's drag profile changed in ways that demanded early commitment. Speed bled quickly once the full configuration was established. The sink rate, already meaningful at normal approach angles, could develop further if the crew allowed energy to erode before the threshold presented itself. The answer was not a correction. It was anticipation. A crew that had fallen behind the energy state could not recover it on a normal approach profile without going around. The throttle response on both the CF6 and the JT-8D required the same discipline. Spool up from low power took time to close in approach. Geometry could not absorb. A crew that called for power at the moment the aircraft needed it was already late. The DC-10 had told you earlier that power would be needed. The pilots who understood it well had learned to read that signal in advance, before the instruments confirmed it. Pilots who transitioned to the DC-10 from narrow-body equipment described a consistent set of impressions. The aircraft was heavier on the controls than anything of comparable size they had flown. The response to trim inputs was deliberate, not sluggish, but it demanded that inputs be made with intention, not reflex. There was a physical quality to the flying, a sense that the aircraft was always present in the seat, always asking the crew to stay ahead of it. Those who flew it for full careers described that quality in terms that were never quite neutral. The DC-10 rewarded precision and it punished assumption. Every time. That honesty was what separated it from easier aircraft. One operational characteristic embedded itself so completely in DC-10 pilot culture that it appeared in every carrier's training program as a distinct discussion item. The center engine's geometry, combined with the aircraft's pitch and roll coupling characteristics, produced a specific behavior during asymmetric thrust conditions at low speed. Go-around technique on the DC-10 was not identical to go-around technique on any other aircraft in its class. Airlines developed procedures, published them in pilot operating handbooks, and trained their crews to execute them from memory under pressure. The DC-10 demanded that its crews carry knowledge unique to itself, and it offered no forgiveness on the occasions when that knowledge was absent. The cargo world recognized what the DC-10 could sustain long after passenger carriers had moved on. Federal Express, United Parcel Service, and a range of international freight operators acquired former passenger aircraft and converted them for overnight hub and spoke operations. The wide lower deck volume, the aircraft's tolerance for varied loading configurations, and its range made it a natural freight platform. These operators flew DC-10s through the 1990s and into the 2000s, accumulating cycles on airframes that passenger airlines had already retired. The aircraft had found a second purpose, carrying cargo through the night on routes it had once flown with passengers. The economics that ended passenger operations on the DC-10 required no dramatic announcement. Fuel prices rising through the late 1980s and 1990s exposed the JT-8D and early CF-6 variants as increasingly costly against the Boeing 767 and Airbus A300. Both offered comparable range on 2 engines and 2 pilot crews. Every DC-10 departure carried a flight engineer who did not appear on the competing aircraft's roster. The 3-crew requirement had been a philosophy in 1970. By 1995, it was a cost. The airlines calculated it and acted. Douglas had anticipated part of this. In 1990, McDonnell Douglas launched the MD-11, a stretched, updated derivative with winglets, revised engines, and a 2-pilot glass cockpit. The flight engineer station was gone. The MD-11 offered operators a modern aircraft and a tested airframe. It was also the last aircraft McDonnell Douglas would produce before Boeing completed its acquisition in 1997. The DC-10 had generated the revenue that funded the program that replaced it, and then the company that built both ceased to exist independently. American Airlines retired its last DC-10 from scheduled service in 1999. Continental followed. United held its fleet into the post-September 11th environment, which made the final calculation unavoidable. The last major U.S. passenger carrier operations wound down through the early 2000s. In Europe, Asian carriers, and across the international network the DC-10 had once connected, the same calculation repeated itself. Newer aircraft, 2 pilot crews, lower fuel burn. The industry had moved, and the DC-10 could not follow it there. As of 2026, a small number of DC-10 freighters remain in commercial operation with specialty cargo carriers. The United States Air Force continues to operate the KC-10 extender in a managed retirement program. What was once a global passenger fleet numbering in the hundreds has contracted to a handful of working aircraft in niches too specific for anything newer to serve efficiently. The pilots who flew it did not need a retirement date to understand what the DC-10 had been. They understood it on approach, in the final miles where energy management was not a concept in a handbook, but a live calculation with a threshold at one end and a runway at the other. They understood it in the briefing that always included a procedure specific to this aircraft and no other. They understood it in the feedback that came through the controls at low speed, direct and unambiguous, telling the crew exactly where the aircraft was and what it would demand next. 3 airlines had told Douglas what the market required. 1 aircraft carried those requirements across 3 decades of commercial service. It was not an easy machine. Demanding was not the word its pilots used reluctantly. It was the word they reached for first, without hesitation, and they meant it as the highest compliment aviation offers.